Hi guys, Dr. K. What I thought we'd do is go over the background for next week's experiment, experiment 15A, the microscale procedure for the extraction of clove oil from cloves. Now, as you probably know, oils are not very soluble in water, and it lends to some interesting results when you do distillation. So let's go into the background of steam distillation of oils. So normally when you have a mixture, the way we normally think of mixtures is we have miscible liquids. So miscible liquids means that if you have two substances A and B and you put them in a solution, they'll mix. And miscible essentially means mixes in any proportion. Well, if you have that situation, then it turns out the pressure exerted by the gas of A and B, for example, this mixture A and B, where their vapor pressures are equal, the vapor pressure of the liquid above the liquid is going to be directly proportional to the vapor pressure of the pure liquid times, this should be mole fraction of the particular liquid that we're using. So for example, if you had 8 molecules of A for every 2 molecules of B, the mole fraction of A would be 80 or 0.8 and the mole fraction of B would be 0.2. The resulting pressure from that, to calculate it, you should take the pressure of A that's pure at a given temperature times 0.8 plus the pressure of B at the same temperature, the pure substance, times its mole fraction, 0.2. The total pressure would then be the sum of those two values. Now, as it turns out, when you have immiscible liquids, and this is what we have when we have oils, this approximation of an immiscible liquids, the two liquids don't mix, and so you have pure A and pure B in a mixture, and the vapor pressure that's exerted by each is independent of the moles of each. So as a result, the total pressure is just the sum of the vapor pressures of the substances when they're pure. So to emphasize then, the major difference is that when you have miscible liquids, when you have miscible liquids, the pressure is the sum of the pressures of the pure substances at any given temperature times their mole fractions. But for immiscible liquids, the calculation is much easier. The total pressure is just the sum of the pressures of each liquid at that temperature. There's a number of ways that this works, but what we'll be doing in our experiment is taking clove, grinding it up, or it may already be pre-ground for us, soaking it in water, and then putting that soaked clove oil liquid mess that we're going to make, and we're going to put that in a 25 ml round bottom flask. You'll add a stir bar, and that's actually a very important point. A stir bar is the only item we have in our kit, really, that is capable of providing a fairly good mass to create a good boiling stone at the bottom. So again, use a stir bar, stick it in the bottom, stir it, okay, to try to break up any of the unusual boiling that might happen. Then on top of that, you'll add a distillation head. Now there's a couple of ways, and I'll show pictures of these in a second. You can use a Hickman distillation head. We've had problems with Hickmans in the past, but we don't actually have enough Y adapters, and there's no guarantee that the Y adapter will help us any more than the Hickman head will. But what happens in a Hickman head when there's bumping is typically it gets up into the trough that's at the top of the Hickman head, and I'll show that picture in just a second. But that gets up in that trough, and then you have a lot of solids that you have to separate out. More traditionally, in a simple distillation, we use a Y adapter and a bent vacuum adapter that you used before for collecting distillate. Again, I only have a limited number of those, so I need to get those back actually this week if you have them. Now for heating, because this is an aqueous solution, I actually prefer using what's called a micro burner. A micro burner is a very small Bunsen burner. Don't use a Bunsen burner, it's too big. Okay, but a micro burner is a very small Bunsen burner that you can use to heat the liquid up. And the nice thing about the micro burner is, especially if the sand bath is taking a long time to heat up, is that the micro burner heats the liquid instantly. The sand bath takes time to heat, but it has a slower, more controlled type of heat. I should also point out that we've been making these blankets to put over the round bottom flasks and conical vials to sort of trap the heat, and I'll show you guys how to make a blanket. This is a perfect application for that technique. So your setups look like this. The setup on the right is the standard Hickman head, and like I said, you're going to put a stirring bar in that bottom part, and then you'll collect the distillate as the distillation goes on up in the trough of the Hickman head. The real problem with this is when it bumps, all that material that's down in the bottom shoots up and gets trapped in the Hickman head. Now, notice the position of this thermometer. The position of the thermometer is just so that it pokes out a little bit into the space above the trough of the Hickman head. That'll give you a fairly accurate reading of the temperature of the liquid as it condenses. Now the other setup is probably a more traditional simple distillation setup. Again, you have the round bottom flask, that's a 25 ml round bottom flask. You have the bent adapter and the Y adapter. It looks like a Y, but it's upside down. And then what you do is you use a conical vial or a round bottom flask to capture the liquid. A 5 ml conical vial might be enough, but a 10 ml round bottom flask is certainly enough. Make sure you put in the O-rings at all these points, otherwise pieces just tend to fall off. And again, notice the position of the thermometer. The thermometer head is just below the Y of the Y adapter, and that again will give you a fairly reasonable temp estimate of the boiling point. One last thing, don't plug that up. That is a vacuum adapter if you want to do a reduced temperature boiling distillation. We're not using that for that, but what that is used for is it is intended purpose for this experiment at least is to allow pressure relief, because otherwise this system is entirely closed, and then when that liquid boils there's nowhere for the pressure to go. Again, if you have this down Y adapter this week, please return. One last thing, I wanted to give you some example calculations of how you might calculate, for example, the mole fraction of the oil in the distillate that you collect. You're going to measure the boiling point, and let's say the boiling point was 98 degrees Celsius. So at 98 degrees Celsius, oops, let me go back. You can look up the vapor pressure of water. And what you find is that the vapor pressure of water is 707 millimeters of mercury. If you want to be more precise, it's actually 707.3, but we'll use 707 for now. Now, if the liquid is boiling at 98 degrees Celsius, that means the vapor pressure, the total pressure above the liquid, is 760 millimeters of mercury, or whatever atmospheric pressure happens to be at that point, or at that altitude that you're at. Well, this is going to be the pressure of the oil plus the pressure of the water. So that'll be the 707. From this, you could calculate the vapor pressure of water as so the pressure of the oil is 53 millimeters of mercury. Now, if you remember that the mole fraction of a substance is equal to the pressure of the substance divided by the pressure total. So 53 millimeters of mercury divided by 760 millimeters of mercury gives me my mole fraction of the oil about 0.0697. Another thing that you might want to calculate is the mole ratio of the oil to the water, and this will help us with the second part of this question, that is, estimate the moles of oil co-distilled from the solution. So if you want to calculate the mole ratio, that is, the moles of oil to the moles of water, you really only have to take the pressure of the oil divided by the pressure of the water. So in this case, that's going to be 63 millimeters of mercury divided by 707 millimeters of mercury. Or a mole ratio of about 0.089 moles of oil divided by moles of water. So I'll just do that as a W. So if you had, let's say, 1 gram of distillate, and let's assume that it is well, if we have 1 gram of distillate and we make a simple assumption that it's about 100% water, because it's very close to that, it's reasonably close to that, I should say. So it's 18 grams for every 1 mole of water. You can then just use that mole fraction that we calculated earlier directly. All right, let me change that. And calculate the moles of oil collected. So for every gram of distillate, I'm getting about 0.0495 moles of oil. And if you know the molar mass of the oil, which you do for in the case of eugenol or clove oil, you could actually calculate the number of grams of oil collected. Now I should point out this assumption that 1 gram of distillate is about 1 gram of oil is maybe not the best. You could actually work this problem out a little bit more accurately by measuring the density of the liquid, or, for example, taking the mole fraction and calculating the percentage of oil in the actual distillate. But for most practical purposes, when you do steam distillation, this is a good approximation that the oil is really not that soluble in the water, so it ends up being, the distillate ends up being mostly water. The other reason that this is a reasonably good estimate is because this makes the assumption that the oil is not actually soluble in the water at all. And in fact, the oil is a little bit soluble in the water, and so that changes the calculations. And there's enough error in those assumptions that assuming that it's 100% water is not too bad. So I hope that helps, and you can always contact me in class or email if you have questions.